So in this class, we're going to look at these two problems. They're coming from an exam paper. Let's see how best we could have answered this. So these are AC problems, and the signature for AC is the presentation of a supply in a sinusoidal waveform. As you can see here, we also have a presentation in sinusoidal waveform. So once we have that, we know to say this is AC. Capacitors and inductors, we saw to say these can be presented even for a circuit which is not necessarily in AC. I think we saw that under that was RC, RL response there. Okay, so let's start with the first problem here. How do we work out this problem? So like every other AC problem, so if the supply is given in AC, you want to change this circuit from the time domain to the polar domain, or to its phasor form. So you want to change, if you have an inductor, you want to change it from looking at it in terms of the inductance to look at it in terms of impedance, so that you can treat it just like any other resistor. If you have a capacitor, you can also change the capacitor and look at it in terms of its corresponding impedance. Then for the voltage source here, you're going to transform it into its phasor form. We'll put a bar on top when we present it in phasor form. In most books, you'll find that they'll highlight it, or they'll make it bold to make sure that they distinguish phasor from the normal one. Okay, so the logic here, first, the problem is asking us to find IT. What did I say? Find the steady state current. Steady state current, this is the IT one. Then after that, they also want us to get the phasor voltage across each element. So we want to get current through each element. They are in series, so the same current will be passing through through all these elements. But they also want us to get the phasor voltages across each element. So what will be the phasor voltage here, there, and there. So how do we do all this? So like as I was saying, to find all those, the first step will be to transform the circuit and look at it in its phasor form. So the first step is to change the inductance to impedance, capacitance to impedance, and the supply to its phasor form. So how do we get the impedance when we're given an inductor, when we're dealing with an inductor? Label this as Z1, then we'll label this as impedance to them. So for an inductor, we know to say the impedance there. So we know it's the complex variable J, and then we have, not necessarily say complex variable, complex number. Here, just keep in mind that J is actually a specific value. It has a specific number, which is the root of -1. So this is if you're dealing with an inductor, and if you're dealing with a capacitor, which is going to be for Z2, we're going to have 1 over J omega, the capacitance. This is the one that sometimes when a negative is put here, or when the J goes up, a negative will be introduced, and then this will be omega C. Some students tend to wonder where the negative comes from when it's presented in this form, but basically it comes from when you try to rationalize the denominator. To rationalize, we're just trying to get rid of that complex number J from the denominator by multiplying the numerator with a J and the denominator with a J. If you did that, the J will now appear on top, but in the denominator, you will have J squared, or J multiplying J, while you still have the omega C. But remember, we did say that J is equals to root of -1. Based on that, this is what ends up introducing a negative in the denominator, because because the square of J there will leave -1 here, because again, J is root -1. So the square of J will mean the square of root -1, which cancels this, leaving us with that -1. So now we have this leading us to j over omega c. So we end up having that. So just wanted to show you where that negative shows up when the j goes up. Okay, that out of the way, the goal is just to see how we solve the problem. Okay, so for the inductor, we have j, the angular frequency. So the angular frequency comes from the problem, and we know to say here the waves are presented in the form V max, and then we have cos omega t plus the phase shift there. So here the angular frequency is going to be the coefficient of the time variable there. Based on this, the coefficient of the time variable in this case is 500. So because of that, omega is going to take the value 500. And then L here is the inductance. Here it's given as 0.3 henries. So this is going to be multiplying 0.3. So now we just have to multiply this. We know 3 and 5 is going to be 15, but then the two zeros will multiply this here, and in the end, we're going to end up with 150. So that becomes the impedance there. Impedance, you can actually look at it as some form of resistance, but just for complex components. So it will still have the ohm there. We do the same thing for the capacitor. For the capacitor, we have 1 over complex number j. It's still the same circuit, still the same angular frequency. So we're still dealing with 500 here. Next, we have the capacitance. So what will be the capacitance in this case? Okay, so from here, capacitance, what we have 40 microfarads there. So microfarads, we want it in farads, not micro. So 40 microfarads, this is the same as 40. In place of the micro, we'll put by 10 to the power minus 6 there, and farads. So this is what is going to come where we have the capacitance, 40 by 10 to the minus 6 here. So here, in the denominator, we end up with that 50. So we now have 1 over j with the 50 here. From here, what comes next? Now we don't want to have a fraction here. So this is where we can rationalize the denominator, and we end up with the minus j here. Oh, no, actually this is after this divides. That is when we end up with that 50. So I actually wanted you guys to give me just the product of the denominator first of all. But I'm guessing you have already gone ahead to divide. And if you divide, this is what reduces to minus j. So the minus is already here. And then the 50 will also be present there. And then this will be in ohms. Okay, so multiply, then divide this into 1. Then you end up with that 50 present there. Okay, so we've seen that the impedance from that capacitor, Z2, has reduced to minus J50. And the impedance from the inductor reduced to J150. Okay, now that we are done with this, the only other element we need to worry about is the power supply there. The power supply is currently in as a sinusoidal waveform. We want to present it in phasor as well. So how do we transform a power source? So as we pointed out, the standard presentation of a sinusoidal waveform, if it's a voltage supply, you have a voltage function of time. Standard to have a maximum, its peak voltage there. Then it works with cosine, not sine, angular frequency, plus the phase shift there. So if you have a supply controlled by this expression, then the corresponding phasor voltage from such a supply will be equal to the peak voltage, then phase, that angle there, the phase angle, or whatever this is what will come here. If it's a minus here, even this will be minus. With that done, let's compare with what we have. Our expression is supply function of time. Then we have 100 here. Okay, can just, okay. So you have 100 there. Then cos 500t plus 30 volts. Okay, so that is what we have there. So from this, to present it now in phasor form, so the corresponding phasor supply voltage, I'll put an S instead of using S there. So the corresponding supply voltage in phasor form would be equal to the peak voltage. Peak is always the coefficient of the cosine expression. So in this case, coefficient of the cosine, we have that 100 there. So this is our peak voltage. Next, the phase angle. The phase angle will come from there. So here we know to say, here a phasor, it only stores the peak and the phase shift. So here the phase shift is 30. So we'll have that 30 degrees coming here. So this is going to be our phasor supply voltage. So our circuit can now be seen in phasor form. How would it look like after transforming it? So now we'll remove everything and look at it now with all these presented using the right expressions. So instead of inductance, we'll put impedance. Again here, this one, we got minus J50. That one remains. Here we'll put the supply phasor voltage. And this one came out as 100 phase 30 degrees. So this is what we have. Now once we transform, what we are now aiming at here when looping is no longer the steady state current. Instead, now when we are looping, what we are getting there is going to be the phasor current. Yes, if the supply voltage is given in terms of in sinusoidal, so it is still sinusoidal, but instead of cosine here, if it is given to you as a sine function, you will have to convert, use the double angle identities and convert that sine function to its corresponding cosine graph. So you'd have to find a cosine function that would have the same shape as what you're given. I think in the last class we had for triple E, we did concentrate on just how we perform those transformations. Hope you guys remember that one. Okay, so with that answered, we were somewhere here and we're saying for this expression, or for this, once we have changed it to this format, the current that we are now seeing here, it's no longer the time dependent one. Instead, we're now looking at the phasor one. So it's no longer the sinusoidal waveform. This is now going to be the phasor current. Now, once you have made the transformation, everything that follows really, it's the same as what we did in DC circuit analysis. So the same rules will apply. Mesh analysis, nodal analysis, Thevenin, Kirchhoff's, everything is going to play a part. So for this case, since we just want to find the current through all the components, we can easily get that current using Kirchhoff's voltage law, or we can even call it mesh analysis here. It's completely up to you which way you want to look at it. Okay. Or if you don't want to go that way and say I'll use mesh analysis, you can still just use the standard way of saying first I'll get the total resistance. If it were resistance you're dealing with, you'd first get the total resistance in your circuit and then use Ohm's law to say voltage is equals to IR, to say that now the current will be equals to the voltage over the resistance. You can still go ahead and use this approach. But I'll use Kirchhoff's voltage law. And from the voltage law, the sum of the voltages around the closed loop must be equals to 0. These are all circuit elements like resistors, so to say. When I find the power supply there, I have minus first. So I have 100, there's 30 there. Then plus 100 ohms. But this is resistance, so I'll multiply it with the current passing through it. So phase current is what I'm dealing with, I, so that I get the corresponding voltage drop here. Then plus, here again, that's J150, multiplying the phase current passing through it, phase I there. And then finally we have this. I want to say plus here, but it comes with a minus. So it comes with a minus. I have minus J150 there. Then multiplying the phase current that will pass through, again, I is equals to 0. The power supply goes to the right. And then these all have I, phase current I. So I can factor out phase current I there. What will remain here is 100. What will remain here is a J150. What will remain here is a minus J. I have 150, 150. One of them is not 150, just 50, which is this one has to just be 50, not 150. So I hope you guys saw that. Okay, so this one will remain as just J50. To the right, this went to the right and it became positive 100 phase 30. So at now, these two of course can interact. So here we have that 100 to be plus J100 here as well, is equals to 100 phase 30 there. Finally, the phase current will be equal to, here we'll have 100 phase 30 over 100 plus J100. So this is where we are. Now, as I was pointing out, you could have arrived at this stage without using Kirchhoff's voltage law. For a circuit like this one, just try it again. These are, we look at them as impedance, but you can still just treat them as if they are resistors. And if they are resistors, you can just say, okay, these are 3 resistors in series. And to get the total resistors, you just add the 100 plus the J150 plus, but now you're adding something which is negative, so it will end up becoming minus 50 here. This would be the total resistance. But again, because these are complex, we won't say resistance, we'll say this is the total impedance. And if you simplify that total impedance there, notice that it will reduce to 100 minus J100. And now when you use Ohm's law in phasor form, the corresponding phasor current for this circuit will be the supply voltage, which is 100 phase 30 divided by the total resistance, which is the total impedance in this case. Notice that this was plus because this was greater, so this will be plus here. So notice that you still end up with the same expression we obtained by using Kirchhoff's voltage law. So whichever approach you pick here should still arrive at the same conclusion. My point here being, the same techniques we used for DC circuits will also apply here. Okay, so now we just want to find the right way of presenting this. If it has to be in phasor form, then it has to be presented as, if it's a current, it has to be presented with the current, maximum current, and the phase shift, like this, not the way it looks like here as a fraction. So how do we do that? Well, we have to divide, because it's like we have two terms that have to be divided. But what are we seeing? They're both complex numbers here. One is a complex number which is given in polar form. The other is a complex number which is in rectangular form. We want to divide them. For us to divide, we must present them in the same language. Well, we can divide complex number with a complex number. So you can convert the polar to complex, but it'll be a little bit tricky to divide. Well, turns out it is easier to divide if both terms were presented in polar form. You see, if you were dividing complex and complex, you first have to conjugate the denominator. After that, then simplify the expression. If you remember the math involved there in conjugating, I keep saying conjugate. Yeah, the complex conjugate is what you use there. But basically, you can still just go with, yeah, conjugate is fine. You'd have to conjugate, and then the process there is not very straightforward. Based on that, we want to avoid that route and say, hey, we'll just change this one also to polar, so that we'll have a polar in the numerator and a polar term in the denominator. Since there, it will be easy for us to actually divide them. So now we want to convert this complex number. So I'll get that complex number, and we want to convert it to polar form. Now, in polar form, we need to find the magnitude, which is going to be the peak value of this polar expression. The magnitude, how do we get the magnitude? You see, a complex number is presented such that it has a real part plus an imaginary part. So here, clearly, x is 100, while y is also 100. Turns out, that's just 100 and 100. From here, if we say x is 100 and y is also 100, from here we can easily get what the magnitude is, because the magnitude of this complex number, we can label it as anything really, we can say r. The magnitude will be obtained by Pythagoras theorem, x squared plus y squared. I wrote y and I wrote the number on the other side. So we'll have this. In the end, this will be 100 squared, then plus the same 100 squared. Basically, the 100 will come out, then root 2. So this is the magnitude. The magnitude has reduced to just that. Now, we need two things, remember? We need the magnitude, which is what will come here as the peak value. We need the phase shift, which is what will come there as the angle. Magnitude has come out. What will be the angle? The corresponding angle can also be obtained from x and y. And in this case, we can say the angle will be tan inverse of y over x. So this becomes tan inverse. X or y is 100. Okay. Well, x is also 100. 100 and 100, that's 1. So you have tan inverse of 1. Well, tan gives us 1 at 45 degrees. So I can go with this one. It can also give us a 1 at other angles, but we can stick with this one. Okay, so we have found what we're looking for. When expressed in polar form, the denominator can be written as 100 root 2 phase 45 degrees. So this is what we can have there. Based on this, clearly, this now can reduce. How do we divide? We're reaching to the part where we're dividing. Remember we said that it's easier to divide polar. Why did we say that? Now they're both in polar. How would we divide them? Well, it turns out in polar, to divide, just divide the magnitudes. These peak values, divide them. So that will just be 100, and this should just basically just give us the same as 1 divided by root 2. How about the angles? What do we do with the angles? Well, it turns out that for the angles, just subtract them. So here, all in all, we can say that if you have the peak voltage there, V1, and the corresponding phase angle there, let's say phasor 1, well, here you have the corresponding voltage, peak V2, and here you have the phase angle theta 2. When dividing here, the answer would be these two can be divided directly, divided by Vm2, but now the angles, subtract them. So this would be theta 1 minus theta 2. So basically this is how we divide if both expressions are in polar. So in this case, when you divide 1 divided by root 2, as it was showed there, that will reduce to just 0.707. And when we subtract 30 minus 45, we get minus 15 degrees. So this becomes the current in phasor form. Now, what is the significance of this current? It's the current that is looping around our circuit. Since this is a series connection, this current is what is going around our circuit, passing through all these circuit elements. The only thing is, it is in phasor form. But we have found it nonetheless. So the question wants us to get the steady state current. Yes, they also wanted us to get the steady state current. We already have the phasor current, but they want the steady state current. They haven't said anything about the phasor current here because they know it's where we'll pass. So how do we get the steady state current from the phasor current? So here is our phasor current. Now from here, remember, it stores two things. It stores the peak value. So in this case, it is keeping our peak current. It also stores the phase shift. So it is keeping our phase shift. So in sinusoidal waveform, if it is a current we are dealing with, we know to say this is going to be the peak current. It's still cosine, not sine. Cosine here, the angular frequency plus the phase shift. You see, the circuit will have the same angular frequency, meaning the same angular frequency we used earlier on, supplied by the source earlier, it's the same one we use here. So from the source, we got 500 rads per second. There's the angular frequency, meaning that that is what we'll keep in this case as well. Of course, the 500T. Then the peak current, as we saw earlier, peak current is 0.707. Next, phase shift comes with a minus. The minus will change this to minus. And then we have 15 degrees there. This is current. The units will still be the amps. So this becomes the steady state current that will be looping through our elements. Next, the voltage drop across each element. So how do we get the voltage drop across each element? Well, simple. Ohm's law, voltage is equals to current times resistance. But for the other elements like the capacitor and the inductor, we will not necessarily look at this form. We can present it in phasor form. So what is happening? Let's start with the resistor. The voltage drop across the resistor. So multiply the resistance value by the current passing through it. Now, because what we have is, let's see what they specified here. They want the phasor voltages across each element. Simplifying our life, since we have the phasor current passing through each element, we can get the corresponding phasor voltage drop across each. In other words, what we'll use here to find the phasor voltage drop across the resistor, we'll multiply the resistance value with the phasor current across the resistor. The resistance value, when we check, that is 100 ohms. There. So we'll have 100 ohms multiplying the phasor current passing through it. The phasor current passing through the resistor is this one. So 0.707 phase minus 15. So from here, you see, this is easy to multiply because the resistance only has a magnitude. You can actually look at it as if it's 100, then phase 0 there. You can look at it like this, which should still be easy to multiply. But all in all, here, this 100 just directly multiplies the number there, the magnitude part. So at 100 with that, we get 70.7. Here we have no angle, implying that the 15 would remain phase minus 15 degrees. So basically, this is how it would reduce. In the same way, what would be the voltage drop across? We can now move on to the inductor. For the inductor, we need the impedance across the inductor. Then we'll multiply this by the phasor current passing through the inductor. For the inductor, the impedance we had J 150. Now we need to multiply this by the phasor current. So again, we see that we are multiplying two complex numbers. One is in rectangular form, the other is in polar form. So still, we're saying that here it is not suitable to multiply two terms which are different. Based on that, we want to present them in the same language. So want to present them in the same language. You can either take them both to complex and then work it out from there, or you can take this to polar as well, then multiply. Earlier on, we did see one where we took that was rectangular to polar. I'm tempted to take polar to rectangular as well, so that you guys can have more to practice with. But in the end, when presenting, I will still want to present my answer in polar form. So I might as well just convert this to polar as well, so that we see, we take the easy way out. Okay, in fact, this perhaps is actually even better because you guys get to see how to handle. This one is a little bit tricky. You get to see how to handle it. Okay, so I want to convert this to polar form. Now I noticed that it only had the imaginary part. It doesn't have the real part. Initially, it was supposed to look like this. So it's like this part for x, it's a 0. But the imaginary part is present. In other words, x is 0. Y must be 150. So here, x is equals to 0, y is equals to 150. So this is what we have here. You see, with the x and the y figured out, we can get the peak voltage from here, or the peak value. The peak value can be obtained, as we saw earlier, by Pythagoras theorem, x squared plus y squared. But with x being 0, this will be the same as the square root of 150 squared. and this will be the same as 150. So the peak value is actually just 150. The only question is, what will be the phase shift? The problem here is, if we tried tan inverse, it would lead us to a problem because y has a value 150, but x is 0. How are we going to simplify this one? So this one becomes not helpful. So we want to find different ways of approaching. Well, x actually can be, if we know r and theta, we can get x by just saying r cos theta, where theta is basically the phase shift we are looking for. So let me actually use phi. Y will, on the other hand, relate to it in this way. But we know x is 0, meaning that we can easily put 0 where there's x. We know r is 150. We can put 150 where there's r, and we're looking for what phi is. So here, 150 times cos phi is giving us 0, meaning that one of these terms should be 0. Well, it can't be 150, so cos phi has to be equals to 150. Not 150, sorry. Cos phi has to be equals to 0. We divide both sides by 150. So for what angles does cos phi give us 0? Well, for cos to give us a 0, the angle has to be 90 degrees, or the angle has to be 270 degrees. But here, instead of 270, sometimes it will be presented as negative 90 degrees. So, in other words, these are the two possible angles that will ensure that cos gives us a 0. But which one are we going to work with? To understand which one we're going to work with, we can look at the second part, y. Y here is given by that, but we saw that y was just 150. R, we calculated it by Pythagoras theorem. It also came out as 150. Then we have sin phi. From here, 150 will cancel with that. We see that sin phi reduces to just 1. So here now becomes our decider. You see, with sine reducing to just 1, it's actually very obvious. Which one of these two angles ensures that sine of that angle will be 1? It can only be this one. Sine 90 degrees will be equals to 1. Sine negative 90 will be equals to negative 1. In other words, had this term here had a negative here, our answer for phi would have been negative 90 degrees. But because it is a positive here, our response for phi will be positive 90 degrees. In other words, this expression can be written in polar. Both terms can be presented in polar. And if we're presenting both terms in polar, we have just seen that this can be presented as magnitude 150, phase angle positive 90 degrees. So it has reduced to this. Okay, so this is what we have. See, when multiplying polar and polar, again, straightforward approach. The magnitudes will multiply. Can you multiply those? What are you going to get? The magnitudes will multiply. The angles this time will add. So when multiplying, remember when we are dividing, the angles subtracted. Now when we are multiplying, the angles add. So when we multiply 150 and 0.707, here we get 106. And when we add 90 plus negative 15, so which is just going to be 90 minus 15, the angle will reduce to 75 degrees. So this becomes the voltage drop across the inductor. In the same way, we can get the voltage drop across the capacitor. For the capacitor, remember, still we're going to use the impedance multiplying the phase current passing through it, the phasor current. But for a capacitor, what did we find as the impedance? We had minus J50. The phasor current is still the same thing, 0.707 phase minus 15. So in the same way, we want to convert this one to polar form. Now do it fast. Can you guys, I'll ask you guys to try to see if you can convert this the stepwise on your own. But by shortcut, after doing this for some time, I know to say that one, the magnitude, the peak value will always be this 50. Secondly, because of this minus here, I know the angle will come with a minus and it will be 90. It will always be 90. So this is what is multiplying 0.707 phase that. So remember what we did, the peak values will multiply. So the peak values will multiply. When we multiply 50 and 0.707, we get 35.4. The angles will add, but this is minus 90 plus minus 15. So in the end, you just end up having minus 90 minus 15. So they'll add up in the negative sense to minus 105. And since this is a voltage, this will be in volts. So the question said the phasor voltage drop across the elements. That's why for these values, we are leaving them in phasor form because they wanted us to find the voltage drops across those. Okay, this completes that question. Do you guys have questions on this one? Okay, so we're going to pause here for tonight. There's still this one. I'll ask you guys to try out this one. AC solve this mesh current approach. So I'll ask you guys to try out this one. We're going to work it out in our next class.